In this case, we're going to be building on your skills that you already have in terms of one, being able to find concentrations of solutions, and two, looking at the lab. You're going to be getting some experience with acids and bases in the lab that you've seen in class, and also the reactions of them, and the difference between strong acids and weak acids. So those are some of the concepts that are going to be developed here. Later in this module, Professor Fine-Weaver is going to talk to you about the kind of equipment that you would be using to do these titrations. And Professor Tatko is going to demonstrate how the software is used in order to take data and find the results of the titration. So in general terms, the titration is a technique that takes a solution where we have a well-known concentration, and we use it to try to find the concentration of a second solution. And the key then is to be able to know that you've had a complete reaction. So the easiest example is the one that's started with also in class, which is a strong base, strong acid titration. And it's straightforward in the sense that when you reach the end point, you'll be at a neutral solution and at pH 7. So we are going to also talk about doing a strong base reacting with a weak acid. And in that case, when we have a complete reaction, all that will be left will be the conjugate base sitting in the solution, and that's going to have a pH that's higher than 7. So some of you will have done a titration in high school, and many cases in high school chemistry, titration will be done with an indicator, that is a substance that changes its concentration or changes its color as the pH changes. And so these kinds of compounds that change color with pH are things that interest me also in my research. But for our experiments, we're going to be doing a little more technologically advanced titration, where we'll use pH to tell us what's happening in the solution, and if we monitor the pH value, it's going to allow us to figure out where that equivalence point is, where we have exactly the number of moles of base equaling the number of moles of acid. So the next thing we should do is look at the figure in your lab guide. Okay, I am looking at the figure that's in the introduction to Lab 7, and I'm going to walk you through some of the ideas that are presented in this figure. On the right, we have a burette that is labeled NaOH. It contains a well-known concentration of sodium hydroxide, and it allows us to know exactly how much volume we've added to the beaker below. The beaker is labeled with HCl. It's a strong acid. In this case, it would be either a concentration we don't know at all, or perhaps it's only known to one significant figure and we want to know it to, let's say, much more precision, that is 3 significant figures, for example. So the titration is going to allow us to figure that out. As we add sodium hydroxide, the pH will change, and so if we put a pH probe inside our beaker and we put a magnetic stir bar on a magnetic stir plate to mix the liquid, we can make accurate pH measurements and follow what happens when we add sodium hydroxide. So on the diagram, we can see how the pH depends on the amount of sodium hydroxide that we've added. And notice that the starting pH is something around 1. And that would mean for our strong acid that the concentration has to be quite close to 0.1 molar. And that would be, for example, the concentration that we want to know more accurately. So as we add sodium hydroxide to the solution, notice that the pH doesn't change very rapidly. We can add 4 mLs at a time, and we see very little change in the pH until we've nearly reacted all the acid. And then much smaller amounts of Sodium hydroxide will give a much larger change in the pH, and the place where we're looking for an endpoint, that is an indication that our reaction is complete, is where this pH changes much more rapidly, the steepest place. And Professor Tadko will walk you through that again a little more detail and with the software to figure that out. But if we know that exact volume and a very precise concentration, it allows us to find the number of moles of base that we added, and we know at the equivalence point that's the number of moles that we had in our beaker. If we know that moles quite accurately and the volume, that will allow us to find the concentration. So that's how a titration works for a strong acid with a strong base. And so let me just describe how this changes a little bit if we're now titrating a weak acid with a strong base. Now the weak acid, if it's a concentration similar of around 0.1, will have a higher pH because it's not completely dissociated. So let's say it starts at a pH of 3 or 4. Then as we add base, it will level off and it'll have a level region of the titration that will be related to its pKa. When we get close to the end point, the pH will likely be higher than pH 7 at the equivalence point, but it'll have a steep place, and we can find a volume that it takes for a complete reaction, even for a weak acid. So that reviews kind of the concepts that are going on with this, this experiment. Titration is quite flexible. We could have a well-known amount of HCl in the beaker with both volume and concentration, and a less precise known titrant, and we can again find an endpoint and deduce something about the titrant. So there's a lot of flexibility in how we arrange what's in the beaker and what's in the burette. And for our particular example, we're going to be using a strong base in the burette and some kind of an acid that we're titrating in the beaker. Okay,